Okay, good. Let's slowly get started. There was one thing I wanted to clarify from yesterday. Specifically here for the analysis in universal hashing where we did, this is good to recap because we'll use it soon again anyways. We used the argument of collisions. In particular, this random variable capital C is the number of pairs, and here ordered pairs. So let me write this even more clearly here, just so that it's more legible. So we have potentially n choose 2 collisions. Every pair of balls could end up in the same bin in principle, and we'll sum up the number of those. Now the expected value of this under a universal hash function, same for a uniform one, is this n squared over 2m, or more precisely n choose 2 or 1 over m. And the lesser equal here just comes because the universality has a lesser equal, but I guess it's going to be an equal in, it has to be equal in the average. So I guess this is an equality in the uniform case. Now, the way we used this argument was then later to say we want to say a probability about this fullest bin, the number of balls in the most loaded bin. And so we said there was some upper bound, and I think we have to smuggle in a +1 here, or maybe play with the strictly greater, some game like that, because we need that the condition in here implies the condition here, so that the probability is only getting bigger. And for that, if you do the calculation with the minus, you need a +1 or some small offset here. It doesn't really affect the overall statement. When n and m are not tiny, then this is negligible. We're using the same argument again. We just started discussing perfect hashing yesterday. Again, the idea to construct for a given set of items a hash function. There's no collisions at all. And we've seen that this is essentially easy to do if you allow yourself many bins. Namely, from the birthday paradox, we know roughly we should have square of the number of balls in bins, or we can afford to throw n balls when n is roughly square root m into m bins without expecting collisions. And so here again, we need this greater equal 2, but this exactly matches, so that we have a random hash function is perfect for with the counter probability, no collisions if there's no bin with at least 2, so then the maximum loaded bin, the counter probability would be maximum loaded bin has at least 2 balls. And so that exactly implies we have at least some collision, and then we can use the bound from before. Now this by itself is not useful because it uses so much space, so we have to work a bit harder to make it into a linear space or a more usable solution. The goal will be to have linear space, and I've already told you yesterday how to do it. We have a top-level function which is chosen from some universal hash function as before. And then this only builds buckets, and then in each bucket we still have to do a secondary hash function. But there I promised we can afford to just use square the size of the bucket as space, and concatenating all of those is supposed to be good enough. So what's the space of this? If we express it as a random variable, what's the overall space that we need for storing the hash tables? It's always n for the top level. Well, I guess I should say the top level hash function uses n bins. Did we write that down somewhere? Maybe let's start with the actual procedure before we analyze it. So the algorithm to find a perfect hash function is, first, we choose h1 uniformly from some universal class of hash functions. And we use n bins for that. So we build a hash table with n bins. And for each bucket, do we have notation for the buckets? I think we only had the size of the buckets. Let's just say for each bucket I, and this goes from 1 up to n. Now we only need to do something if there's some elements in there. If there's at least 2, then we draw a random hash function, hash2. And superscript I. From another universal class of hash functions. I mean, it could in principle be the same, but let's say it's some h prime, again, universal. And this we repeat, I should say, with xi squared. Sorry, xi is already the number. Xi squared bins. Repeat this until this hash function is perfect. And that's the part we already analyzed. That takes a constant number of repetitions in expectation. And that's all. So the output then is the hash function that we get from the inserting. So we output this as a function, or plus the hash tables. I guess we just built the hash table. But there's one more step here, in that we repeat the entire construction. I guess we can smuggle that into step 1. I don't have to move that. Until the number of collisions is not too big. And less or equal n should be good enough. So that's the algorithm we're proposing. Now we have to show 2 things: that it succeeds with good probability, or the number of repetitions is reasonable, otherwise it would run forever. And we have to show number of repetitions is small, and we have to show, not confuse that with the algorithm steps, and we have to show that the space usage isn't too big. That's the two things we need for this algorithm to be useful. And both is a relatively simple argument, so I'm trying to squeeze it into the part of the slide so we can still see the algorithm while we're doing it. For part A, we just use that the expected number of collisions we get by the same argument as before, because it's a pairwise independent function. Each of the pairs has probability 1 over n to collide, and so the expected number of collisions is just n minus 1 over 2, which means the probability that we get less than n collisions is going to be at least 1/2 by Markov. So we, in expectation, only need 2 repetitions for the topmost step, and for the part for the steps 2, that was in step 1. And in step 2, this is analysis from before. I'm just going to say C above, same result. Expected number of repetitions is 2. So over all of those repeated steps, we're going to get time proportional to what it takes to do one of these random samplings, and these are all fairly fast. So the overall expected time is going to be what? The time to draw the random functions is actually small. We have to compute the bins, and we have to find the functions here. So I guess it's going to be linear. Now for the second step, the space usage, if it succeeds the way we defined it, is upper bounded deterministically. The space we use is the space for the hash table cells and the hash tables, the hash functions. But that's, say, for the classes we looked at, that's 2 numbers per hash function. So we have linear, that's for the top level hash function, for the top level hash table, and all hash functions. And then we have a part that comes from the secondary hash tables. And because these all use xi² bins, what we get is the sum over all the bins, xi². Now that seems potentially scary. All we know is that the number of collisions is bounded, but we already know how these relate. Because, okay, tiny side calculation here. We've established that from a single full bin, we get xi choose 2 collisions. So if we have xi², that's almost this. Right, this is xi² over 2 minus xi over 2. And so we're going to rewrite this as the linear term from before. Might run out of space. We'll see. The space analysis runs out of space. Then we have the xi choose 2. And we have plus these guys. Now the second part here, that's summing up the sizes of the bins and divides by 2. So that's going to be less or equal n, or n half really. So that part goes into the theta of n bit. And this other term, well, every bin causes exactly that number of collisions. So what we're summing up here is all collisions. This is exactly our C. And C we assume was bounded by n as well. So in total, the overall space is theta n. And that just follows from the construction. The random part was just the time. So in a way, it's a Las Vegas algorithm with respect to how much space it uses. That's always fixed. And the running time, because of the repetition, is random. That's all on perfect hashing. With this combination of very simple tricks, you get some result that may at first seem relatively hard to even imagine that it's possible. But really, all of these we have achieved. The hash functions, we can pick our favorite pairwise independent hash functions from the random lines modulo prime. So these are easy to store as well. And we can construct a perfect hash function of using a linear number of overall space in linear time. So all of the requirements are fulfilled. And all that we needed is some clever random sampling and the 2-level scheme. That's the end of the hashing part. Are there questions at this point? Also on Slido, of course. Okay. If there are no questions on hashing, then make a pivot to a different topic. In the next section, I want to come to visit a problem that is almost as old as algorithms are, but also one that specifically randomization has a key role to play in. That's the question of deciding whether a number is prime. Before we'll come to that, a few comments on the design technique that underlies the algorithm we'll look at. And that's this aforementioned abundance of witnesses. So again, framed it again a bit from the complexity theory perspective. If you have some language in NP, then you know there must be some certificate for every word in the language that certifies that that's in the language. If we have that certificate at hand, then it must be efficient to check. Now, in general, this is not always true for everything in NP, but suppose that it is true for our specific language, that there are many certificates that actually show that X is in the language. That's an assumption we're making here, but we'll see examples. If that both is true, then it makes sense to try to just randomly guess some string and check if it is a certificate. Maybe we're lucky, and then we'll quickly prove that X is in L. And if we've kept going for a while and we couldn't find any certificate, then maybe we can conclude X is not in the language. That's the idea in abundance of witnesses. You hope you have a language in NP where there's many certificates, and so either you find one, or if you don't find one, there's a good chance that there is none. So the input is not in the language. And let's apply that to a more concrete problem. So given some number n, all we want to know is that a prime number or not? It can be traced back a lot in time. People wondered about this for a long time, and it's only fairly recently been properly resolved in a way. Let's first look at some simple approach that you've probably seen in some introductory classes, often a good intro algorithm. How do we find out if a number is prime? Well, if we've tested all potential factors and none of them divided the number, then clearly it is a prime. And more specifically, we can test all prime numbers below square root of n. These are the only actual candidates or the only interesting candidates for factors. The number might have more factors, but if it has any factors, it will have one of those, a prime number below square root n. Right? Square root n is clear. Any factor will be either below square root n or number divided by the factors below square root n. So checking for one of the two is enough. And we can restrict the attention to primes, because if there's a non-prime, then it has a factor, and then we could have, well, taken that factor instead. But in a way, this sounds like we're trying to solve the problem by solving the same problem, which sounds a bit contradictory, right? We need to know what a prime. We need to know primes to check if a number is prime. But of course, there's no contradiction, because you can do an inductive algorithm. And in particular, there's a clever algorithm you will have seen, the sieve of Eratosthenes, which gives you all the prime numbers up to a certain threshold in a somewhat reasonable running time overall. And here's the algorithm itself. It's basically, it's called a sieve because it goes through all the numbers and kicks out those that are composite, that are clearly not prime. And it effectively goes through the numbers from small to large and then crosses out all multiples of a number. You can be a little smarter. So first of all, you iterate over the numbers, but then if you already know that a number is prime, then you have to do it. Otherwise you don't, because you'll have a factor that already crossed out all your multiples. And also with the multiples, you can start at the number itself. So you start with the square of the number, because all smaller multiples will have been caught by the smaller multiple as a number. Think about it for a minute and you'll see why. So that's where we can start, and we go up to a point where we would overshoot n. And then we take the product, the multiple of I, and mark that as not prime. And then we, if we've done all that, everything that is left must be a prime number. So that's finding primes up to a threshold. If we want to test the number for primality, what we do is we compute all the prime numbers up to square root of the number and test all of them. Easy. How good is this? The time of the primality check clearly is dominated by finding the primes. And how long does that take? It's actually a subtle analysis, if you want to be precise. So the time to find all the primes up to number m is, well, m for going through the loop, the outer one. Sorry, up to n, but I'm setting m as square root n. So you go through this loop m times roughly, and then for each prime, you have to go through that many iterations of the inner loop. I'm kind of not analyzing the starting at I part. That one is a clever trick, but I'm just ignoring that here. So it's just an upper bound. But doing this sum where you have to do a summation where you only do the prime factors. That's tricky. So we can make our life easy and get an upper bound by dropping that restriction. And then at least you get harmonic numbers, so m log m time. Sounds not too bad if you write it that way. And if you do actually make the analysis more careful and take into account that you only have the prime numbers here, you can show that it's m log m, really. That seems to be more technically involved, so we're not going to do it. And the space, of course, is maybe practically speaking more of a problem. Now, all of this sounds okay, right? M log m, we've been happy with algorithms of that running time. But of course, the problem is here that this is a number, and we would encode that in binary. So even square root n is an exponential in the actual input size. And I think if you take this primality check and apply it to prime numbers as you would use them in cryptography, it's not going to be good enough. You need some smarter techniques. Okay, but that's kind of the trivial algorithm to do it would work like this. And it's not completely useless, but it's going to be exponential in the input size. So the question then quickly comes up, can we do much better? What's the complexity status of these problems? And so with these problems, I've not defined the problems. Let's do that here. There's two problems. There's the problem primes. If you think about a language, that's the set of numbers that are prime. So we're given an integer in binary, and we want to check yes, no, is that a prime number? And you can also use the search problem of this decision problem, the integer factorization problem, where you're given an integer, but then you either want to find some non-trivial factors, which prove that the thing is not prime, or you output it's not prime, it's prime. In which case, we don't require a certificate in the problem of integer factorization. Okay. As you may see from this immediately, if the number is not a prime, then the factorization is a certificate. So we can conclude that primes is in co-NP because the no instances have an efficiently checkable certificate. What's not clear is if the yes instances also have a certificate. How would you prove to me that a number is prime other than saying, I've tried all the factors and none of them I've tried all the numbers and none of them is a factor. That seems less clear. So whether primes is in NP is already a bit unclear from the definition. Also a good point to make the connection to the very far beginning of the lecture. The running time of the sieve of Eratosthenes is, of course, pseudo-polynomial. Right? It's polynomial in terms of the number of things in the input, but it's only pseudo-polynomial if you take the binary encoding. Now what we'll show is a slightly better result. So here, the fact that it's in co-NP is not practically useful, right? We don't expect efficient algorithms for all problems in co-NP, same as for NP. But we'll show that you can do a randomized test, a randomized primality test, or compositionality test, I should say, which also shows that the problem is in BPP. And we've already seen BPP is likely to be the same as P. Now, in this case, we don't actually need to invoke these kind of arguments. If you're just curious about the complexity status, it's been in this millennium, but a while ago by now. As a major breakthrough, we know now deterministic, unconditional algorithm that runs in polynomial time and decides whether a number is prime. And there's also a notion of certificate in a way that the algorithm can prove to you that a number is prime without just exhaustively going through all factors and showing that these are not numbers and showing that these are not factors. There's clever number theory behind it. Crucially, this is not clear for integer factorization. And everyone working in cryptography knows that the classic cryptography really relies on factorization being hard. We know that it is not hard on quantum computers in the theoretical way to define them, which I think the largest number factorized on a practical quantum computer is 6 or so. It's they're not quite there yet. But in terms of the computational complexity, we don't know. Integer factorization seems hard, but we don't know. Maybe it could be in some sneaky way allowing us some efficient algorithm, and we just haven't found it yet. That's just as an aside. So what I'm showing you is not the state of the art. For checking primes, in principle, you can do deterministic polynomial time. Now, the algorithm itself is complicated enough, and I think the degree of the polynomial is n to the 6 or so, and it's not clear if you can do this much better. So practical implementations will very much use these randomized algorithms that we'll look at, or slightly cleverer twists of those. So does primes have this property that we have an abundance of witnesses? Let's try the obvious. And really, I should have said not prime here, because as I said, there are certificates for primality, but these are tricky. So what I mean is, can we expect to easily find factorizations for a non-prime number? If we just look at the factors, the obvious approach to certify that a number is not prime, that's not going to work, right? There's numbers that are just there's composite numbers with just 2 large primes as a factor. And so finding these is needle in a haystack. That's not going to work with randomly guessing numbers. Also, that's hardly or it's hardly a promising approach. Because if that was possible, it would give you a factorization. Right? If I can guess a factor, then I can produce the two. I can produce a factorization of my number, proving that it's composite. And we've just discussed that that is unlikely, or seems hard to do. So we have to work harder, and we'll have to use something that indirectly certifies that a number is not prime, but without explicitly giving you a factor. That's weird. How would that be possible? Enter a number theory and modulo and finite fields and so on. There's various tools you can apply there. The simplest is Fermat's little theorem, which just states what is written here. For every prime and a number between 1 and the prime, you could check that raising that number to the prime power -1 is going to be equivalent to 1 modulo p. And so I'm not going to dive into any of the number theory parts here. So we could try to pick a random A in the range. So we're given some number p for which we want to check if it's prime. Right. So I guess checking means we compute this power modulo m, modulo p. And this exponentiation sounds expensive, but you may know if you do it modulo p, there's actually efficient algorithms, because you can always do modulo p because it's a field, so you can compute in the small number field where everything is staying below p. So, and if that is not equivalent to 1, then we know p is not a prime. Okay. This is indeed sometimes used. It's called the Fermat primality test. It has one problem that maybe some people know about. This is an implication. If we have a prime, then this holds. It's not an equivalence. So given that mathematicians try to be as precise in general as possible, if it's not formulated as an equivalence, there's probably some counterexamples. And in this case, it's famous enough. These are called the Carmichael numbers. Which satisfy this but aren't prime. Let's just give that a name here so I don't have to copy it. So the primality test here is relatively straightforward to do, but it has this blind spot, or well, infinitely many blind spots, where it would erroneously say something is a prime because this is satisfied, but the output should really be, it's either prime or a Carmichael number. So can we do better? We need a more famous mathematician. Let's use Euler. There's a criterion that's named after him, at least. If we have any odd number greater than 2, now this time it's a proper characterization. This number is prime if and only if the following is true. For all numbers in, so this is I don't know, it's the finite field of the integers modulo p. That's what I mean by this. So if we take any number not 0 and take that number to the p minus 1/2 power, so that's why p has to be odd. Otherwise, this is a bit of a trick, a problem in integers. Then taking that modulo p has to be either 1 or -1. And if that's true for all numbers in this field, then p is prime. That's an if and only if now. So it's a bit more convoluted how to use that. But at least now we could check this. We won't want to check it exhaustively because that's a lot of numbers if p is big. But we could check random a's and hope for the best, right? If again, if we find an a where this is violated, then we immediately know p is not prime. If we checked a lot of a's and they all satisfied the criterion, we could try to do the generalization and say maybe all of them do it. So let's claim p is probably prime. Question? Yeah, I guess it's p minus 1. Just like I should probably have. There's no nice element symbol that corresponds to the equivalence. It's a bit more memorable to write it that way. Yeah, thanks. Please ask questions if it's not clear. Now this could work, but there's one catch, which is, does this have this property of abundance of witnesses? And that's where things get slightly tricky, but is not too bad. We'll just look at the easier part. So I'm assuming that I'm given a number that's not just odd, but also n minus 1/2 is odd. So it only works for half of the odd numbers. Then it's easy to show with this criterion that, well, first of all, if n is prime, then that has to be true for all of these guys. That's from above. But if n is not prime, then at least half of the numbers a from the set here give a result that is not in 1 minus 1. And so if I pick a random a, I have a chance of 1/2 to pick an element that shows this. Again, the proof is more number theory than algorithms. So I'm basically skipping this now for interest of time. You can show that you have some injective function from the numbers that are not witnesses to the set of witnesses, so you can pair them up in a way. And so the number of witnesses can't be smaller than the number of non-witnesses, where a non-witness here would be a number that's in this set, 1 minus 1, if you take the power. From this, you can build what's here called the simple Solovay-Strassen primality test, because it has this restriction that it only works for half of the odd numbers. This is a restriction you can easily lift, but again, it's more number theory than algorithms. The algorithm is as you would expect, as I described. You pick a random number from the allowable range, you compute this power modulo the number, and then just check if the number is in the expected set for a prime, then we output it's probably a prime number, and otherwise it's not a prime, and this is for sure. So it's basically we've already proven that this is a one-sided error Monte Carlo algorithm for the compositionality problem. So if I give you a composite number, you'll probably find it with probability 1/2. If it's not composite, namely prime, then you'll never gonna err on that. Now, one-sided error Monte Carlo is good, but for the wrong problem, for the composite problem. Now, if you want to formulate it as a primality test, then we can call it a two-sided error Monte Carlo, where the error is in the other direction. That's all that the corollary says. And this restriction is just a reformulation of this condition. I'm going to leave it with that because I'd rather show you some interesting algorithm for satisfiability. There's one last thing you can do with this, apart from checking for primes. You can also use this to find a prime number, or sample a random prime number, which is often a building block in other algorithms. The algorithm is relatively simple. We keep trying for a certain number of attempts. We generate a random bit string and interpret it as a number. It's a bit of a slightly convoluted way to say that we generate a random odd number, but I wanted to explicitly show that you can do this from random bits. Maybe this is not so surprising. Then we run the primality test also a certain number of times, just to get more confident in the output. Probabilities boosting, and if any of the outputs says this is not a prime, then we try again. So we increase the number of failed attempts, and otherwise we can output our prime number because we probably found one. Okay. And we fail if we've used up too many attempts. let me state the theorem, but I think I'm also, in the interest of time, skipping the proof here. So the claim is that if I call this with twice the same parameter, then I get a two-sided arrow Monte Carlo algorithm for generating primes. Where I'm using I guess that's L here, where I'm using roughly L bits. Now, some of the leading bits could be 0, so I guess it's a prime number of value at most 2 to the L. What you have to show is, 1, that the output is usually a prime, and 2, it doesn't fail all the time. That's the 2 claims. The fact that it uses enough repetitions on an algorithm that has an error of 1/2 just means it's gonna have an error of 2 to the minus k. Is actually stronger than what we would require for just Monte Carlo. And it doesn't fail with this statement, no prime number found. With the probability of 1 over 2L. So again, much stronger than what we need. So you could reduce the number of iterations if you just wanted the 1/2. The only interesting part is we're picking a random odd number. How likely is that to be a prime? Let's ignore the second part. We're also checking for primes with a potentially faulty method that sometimes doesn't. Which way around is it? It may sometimes say it's probably a prime, but it may sometimes erroneously say that. Okay, so it's a bit in the 2 directions. But let's suppose this test was perfect. How likely is it that we hit a prime number if we just randomly sample a number? So apart from the standard analyses we've done many times, so we actually forced the first bit to be 1 here. So the n is sampled uniformly in the range 2 to the L up to 2 to the L minus 1 up to 2 to the L. So it's a random odd number from that range. How likely is that to be a prime number? And so this is where you need an ingredient from number theory again. And this, I think, is useful enough to at least roughly have in mind. prime number theorem. You likely saw some statement of this in some introductory module, but often not formulated in the computer sciencey way. Pi of x is a function which denotes the number of primes less or equal x. And the prime number theorem says that this is asymptotic to x divided ln x. Okay. And so, well, what does it mean? The fraction of numbers which are prime is going to 0 because out of x numbers, only x divided log n x are prime. But also is a fairly large fraction. I always found that surprising that there's so many primes. Also, the number of primes, if you look at the distance between two consecutive primes, this is like a very chaotic sequence. Sometimes you have these twin primes where the distance is just 2, and I think it's still open whether there's infinitely many of them and all these things. And then there's sometimes long jumps between primes. But if you smooth things out by integrating, just counting how many primes are before a certain point, then you get a fairly clean and simple description that at least asymptotically gives you a nice number. And so you can maybe now imagine you have from this range, there's going to be roughly 2 to the L divided L many primes. So you have a chance of 1 in L to pick one. So you have to sample L times in expectation to get one. I'm not going to do the full math here. It's something we've seen a few times now. So the overall running time for the algorithm, I think, is maybe useful just to state, because L to the 5th is also not that great. Okay. So I just wanted to throw this piece of knowledge out without much more content or more context. Okay. Maybe now is a good time for a little break. We continue. Oops. How long does this go? The tips of these pens are surprisingly sturdy. I've been dropping it a couple of times now and it's still going okay. Sorry, were there questions about the primality part? I'm trying to rush a bit because I don't want to cut too much into the approximation chapters. But I think we're already kind of a bit behind. Yeah. I think the answer is probably no. I don't know. It could be. I've been peculiar about picking here ln, right? It's a natural log that comes out here. I'm sure there's a lot of intuition to some of this. That's right. Yeah, true. I'm not sure what what a good intuition behind that result is, to be honest. The connection to sorting maybe is spurious because sorting really has a log base too. If you think about the comparison lower bounds and these things, the algorithmic reason why ln sometimes pops up is from harmonic numbers, right? But there it's kind of just the asymptotic approximation of harmonic numbers uses this log. Sure. Yeah. A lot of stuff goes to zero and at various speeds. Yeah, I think that's the surprising bit, given that the distance between consecutive primes is so unpredictable that averaging over the prefixes is so clean and easy. But I think the asymptotics here also hide some not so clean and easy parts. And I don't think I remember a proof of this. I don't think I've ever seen one. It might be a bit of a lengthy tour to get there. Oh, it's asymptotic equivalence. That's rigorous. No probability stuff. But it might, so you could rewrite it as equal 1 plus little o of 1 as x goes to infinity, which means if you take this guy and divide it by this, that's going to converge to 1. Also means this 1 over log n of x, that's the truth, right? That's the true asymptotic proportion of prime numbers. Yeah. So you're basically asking what's the rate of convergence or what's this little o of 1? And the answer is I certainly don't know from the top of my head. This is clearly known to some degree. So maybe it's something to look up how many more statements you can make about this. But it's just I think often when you do some intro math, discrete math, number theory things, they don't often formulate it in this asymptotic sense right away. And so the message that for computer science is so useful gets blurred a bit. But of course, they also want to get the proofs. We have this is some really cool stuff. I'm not going to skip the satisfiability part. I might skip this chapter after this if we run out of time. There's a cute algorithm, but maybe you can survive without. Well, okay, that's putting the stakes high, but I think this one has all that's needed for a cute result. Useful techniques in the back and some broad and important problem. In the next section, we'll again make a little pivot to a very different problem. We're going back to NP-hard problems for sure, and try to see how far we can get with randomization, even if we shouldn't expect to get down to something polynomial time. Maybe we can do something that's not so easy to do without randomization, and I think it's true in this case. Also, the strategy is much more versatile than this specific problem, and the analysis technique also is much more versatile. And so I think for that purpose, rather than specifically the result about satisfiability, this is worth having a look at. We'll again use random sampling in a specific way. What we've so far seen is if I'm trying to solve some problem and the solution is tricky to construct in a targeted fashion, say perfect hashing, perfect hash function, then I might try random sampling if I know that there's many possible solutions. It's just a little tricky to get one specifically chosen. Then we can just try this. What we'll now use is random sampling when the object itself is rather rare or rather hard to find, and we still want to somehow do something non-trivial to improve upon the brute force search that just tries all possible alternatives. And surprisingly, this is possible. What we'll need a bit to set up the methodology is a tiny detour where the problem we're solving is not actually a hard problem. And that's the 2-SAT problem. You remember 3-SAT as the NP-hard problem. Let's look at 2-SAT. Sounds suspiciously similar. We're given a CNF formula where now we have at most 2 literals per clause, not 3. Why would that make such a big difference? Well, it does. This is a problem in P. And the reason is that if you have 2 literals, you can rewrite the clause as implications. It's just the good old A implies B is the same as not A or B, and then you apply this with the right negations. So any such clause with 2 literals can really be seen as 2 implications. Also, just from the logic, from the semantics itself, if L1 was not true, then to make the whole thing true, L2 has to be true. That means L1, not L1, implies L2. And also vice versa. What this means algorithmically is that we can represent the whole formula as a graph where the vertices are the literals, which means the variables and their negations. That's all the vertices in the graph. And we have edges whenever there's an implication coming from some clause that means one thing implies another. And now we can try to satisfy the formula in the graph by picking certain vertices where we make that literal true. And we could try to just randomly pick a vertex, make that true, and then follow the outgoing edges, which give us implications. I also have to pick those vertices and set them to true. And that has more implications. I'm kind of going through the graph. Now, if I just do this planlessly, I might end up in a cycle. And then I could end up in a problem. The cycle might mean that some xi wants to be set to true, but then there's a cycle back to not xi, which also wants to be set to true, and then I'm not so sure what I should do. But if you think about this problem for a bit more, you can show that if such a situation happens, that there's a cycle from xi to not xi, that's actually always an indication that the formula is just not satisfiable. So if you ever run into this problem, there is a real fundamental problem that you're not going to get around ever. And if you don't run into this problem, you'll just find a satisfying assignment. You can make, instead of just starting at some random point and see where it leads you, a more efficient way is to use strong connected components. These can be computed in linear time with algorithms that you may have seen in undergrad. There's essentially a depth-first search behind it in a clever combination of depth-first search. So you could find the strong connected components, check if in any component you have both a variable and its negation. In that case, you have a contradiction, and you can just say there's no satisfying assignment. If that's not the case, then again, you know from strong components, if you contract every component into a single vertex, the resulting graph has to be a DAG. And so you can go through that DAG in topological sort order and satisfy all, and find a satisfying assignment by just starting at sources, satisfying them, and then following the implications. I've just run through this algorithm very quickly. If you've never seen this, maybe it's almost impossible to understand. My point was really just to say, this algorithm is in P. We already know a simple solution. It's actually a linear time solvable problem. So what comes now is not so useful by itself. It's about illustrating the technique. What can we do to find a satisfying assignment if we don't want to invoke any kind, we don't want to do any thinking, okay? No implication graphs, no strong components that make my head ache anyways. So let's do something random. First of all, we choose a uniformly chosen random assignment, which most of the time is not going to satisfy the formula. But let's try either way. If it currently does, then we're happy and we return it for sure. Otherwise, there must be some clause that's not satisfied. So there's two literals, and they're both false at the moment. So I'm going to pick arbitrarily one of them and make it true by flipping the assignment for that variable. And that's going to be my new assignment. Maybe I'm lucky and that satisfies the formula. Probably I'm not, and I just keep trying. It's a completely mindless way of solving this problem. And in a way, this shouldn't be allowed to be successful. But again, the two-sat problem is tame enough that it actually does succeed in a way. First of all, what does succeed mean? If I ever find a satisfying assignment, then I'm clearly proving that the formula is satisfiable. If I do this for a certain number of repetitions, we'll come back to this confidence parameter, then all I can say is that probably the formula is not satisfiable, right? It's a Monte Carlo algorithm. Now, the running time is not hard to analyze because these are just explicit loops. So you're going to run through things a couple of times. The number of loops, say the confidence we put to some constant for now. The number of loops is essentially quadratic in the number of variables. And all we do inside is pretty cheap. So it's not as great as the well thought out linear time algorithm, but at least not super far away. And indeed, we can prove if we're given any two-sat formula and it's unsatisfiable, then we'll always output not satisfiable. But if it is satisfiable, then with high probability in terms of this confidence, we'll find a satisfying assignment. Okay? And yeah, the overall running time, I didn't even put on the slide. Is there anything interesting happening here? So this will take linear time in the formula if you do it naively. So I guess it'll be k squared times the confidence parameter, and then times the length of the formula, say n for that. But the interesting part is to analyze this. Okay. The first statement we're not going to prove, that's obvious. If there's no satisfying assignment, I can try searching as long as I want. So clearly I won't find one. The interesting part is to show that I have a good chance of finding a satisfying assignment if there is one. So if the formula is satisfiable, that means there is at least some alpha that satisfies the formula. And I'm going to stick with this worst case that there's a single assignment making the formula true. In general, it could be many, but we'll just fix this one. And everything will be analyzed in terms of this worst case assumption that that's the only one. Okay. Then the algorithm is obviously running in iterations. So it'll compute different assignments in the different time steps. So let's say alpha t is the variable assignment in the tth iteration. And t clearly runs from 1 up to this confidence times, was it 2k squared? Yeah. Okay. And so the interesting parameter will be how far are we in these assignments that we try away from the satisfying one. And specifically what we'll look at is just the Hamming distance of our satisfying assignment, the single one that we pick, and what we currently have. That's a random process, and you can go up and down, you can go whatever, right? Hamming distance just means positions where they differ. So the number of variables where they differ. And so let's make a few obvious observations. If we ever have, okay, is to stay consistent, let's flip this around so we use k minus the distance. Then it's a positive thing to improve. So xt is our current, the number of variables that we correctly guessed. If we reach k, then we're happy. We found our satisfying assignment, and so then we can stop. Otherwise, we're going to keep trying. So what the algorithm does in this case is it finds a clause that's not satisfied and picks one of the literals and flips the assignment. So I'm going to change the variable assignment of a single variable. That's going to get my xt plus 1 either one better or one worse. I don't know which one. Of course, at the boundaries, if I'm somehow unlucky and I made every variable 0, then the -1 is not possible. But it's always going to be true that one of those two options is what happens. Now, what are the probabilities for these two outcomes? Sorry, xt plus 1. Let's focus on the good things in life. So what's the probability that I'm going to end up with the next with an improvement. If you look at what we're doing, we have an unsatisfied clause. Currently, these are both in the wrong assignment. So there's different possibilities what alpha can assign to these variables. We could have one of them guessed right, or we could have both. We could have none of them guessed right. Right. So in this unsatisfied clause C, could have 2 incorrect or 1 incorrect. If we guessed only one variable incorrect, then the probability 1/2 will improve. With probability 1/2, we improve. Come on. And if both were incorrect, then we always improve. Amazing. So with probability 1, we improve. So we don't know which of the two happens. All we can say is with probability at least 1/2, we're gonna see an improvement. And that's why 2SAT is easier. If you think, we'll apply the same trick to 3SAT later. There you have 3 literals. That's 3 literals, and you don't know. In the worst case, you could have just one of them guessed right, guessed wrong, and you have to somehow hit 1 out of 3. That's going to be less likely. So it's less than 1/2 probability potentially to make an improvement. Whereas here we have at least 1/2. And so at any point in time in 2SAT, it's more likely to improve your assignment than to make it worse. And that's, I guess intuitively is making it much more likely to see improvement after improvement. Okay, we'll come back to that if that didn't help you too much. Also, the starting point x0 is any number between 0 and nk. We don't know where we start. In the worst case, we start at 0. Yeah, it won't ever get worse than that. And so we'll analyze this worst case in the following. Okay, how are we going to do that is, first of all, we note these transition probabilities, what happens to our assignment, and particularly this random variable of how many variables we have already assigned correctly. This is a Markov process, because all that comes next depends only on how many I've guessed correctly so far. In the way I've described it here, that's true. You can say it's a Markov process for the entire assignment. But for the behavior of how many we guessed correctly, it only depends really on the previous xt. Or at least we can say the true process is never going to behave worse than a Markov chain that only looks at the number. Yeah, how can we write this formally? Okay, let's first say yi is the expected number of steps I take to reach this alpha star. And now potentially you can allow to run this process forever without this explicit upper bound here. You just keep it running. It will eventually find the right assignment if you just keep going, if there's no other way to terminate. Let's give this another name. In the actual algorithm, this is the number of steps, S, and it's a bit more subtle. We don't know exactly what this number will be, but this is always going to be less than the number of steps from having xt equals I, or just let me just say from I correct variables, I correct assignments. What I want to say is that we're simplifying and we're just making this an equality. Let me just write it like this. I want to distinguish the steps that the algorithm actually takes from a simplified random process. Oh, great. Okay. Okay, sorry.